Okay, students, let's go ahead and dive into the lecture on Chapter 11, how we use energy and the transformation of energy. Now, and hopefully most everyone should know this from middle school, and I think they even teach it earlier than that in probably the 4th and 5th grade. You've probably been hearing this since then, or I hope you have. Law of conservation of energy basically says that we cannot create or destroy energy. However, we can change its form. We can transform it, okay? Now, when we use the words lost as not lost there, we have to use those kind of carefully. Energy's never lost, but many times in transformations, during the transferring process, the energy, some of it is not able to be recovered. For example, when you drive a car, if you've ever noticed, the engine gets very hot, okay? Well, that has a lot to do with the combustion in the pistons. It also has a little bit to do with the friction of the parts moving. There's not much friction, but a little bit. And the engine, of course, warms up. Well, that releases thermal energy. That thermal energy is in the atmosphere. We're just not able to get it back, okay? So when we say not lost, well, we need to understand that during the conversion process, many times energy is some of it is not able to be regained, okay? So again, we don't destroy or create energy, but we can transform it. Here they talk about soybean oil being turned into candles, the energy within the carbohydrates, not the carbohydrates, the fats and the oils within the hydrocarbons, that's what I meant to say, is converted into light energy and thermal energy, okay? All right, now, same thing here. We take wind. The wind hits these huge windmills, wind generators, and converts mechanical wind energy into electrical energy, okay, by mechanical means, okay? Kind of the way a dam works, hydroelectric dam, except uses water, but it's the same process, okay? Now here's a very familiar equation you saw from last chapter. Of course, the total energy, this is what we call our work equation. The total change in energy is equal to the sum of all energies involved, which is equal to work. So we could technically say that the change in the total energy is equal to the work, okay? And remember, in an isolated state, the work is equal to zero, okay? So don't forget that. Now, when work is positive, and this is very important to remember, when work is positive, when we say it's transferred into the system. So if we're putting energy into the system, then that's positive work. If we are removing it from the system, then it is negative, okay? So you need to remember that. You need to make a note of that on your note card, that transforming energy, when work is going in, it's positive. When work is coming out, it is negative, okay? When other forms of energy are transformed into thermal energy, this change is irreversible. Again, the energy isn't lost, but it's lost to our use, okay? And what I was just saying, I was getting a little ahead of myself a minute ago. So please understand that. So when you convert chemical potential energy inside those cylinder walls, inside those cylinders on your engine of a car or motorcycle or lawnmower or whatever, you've got to realize something, that when it changes from chemical potential to mechanical, then some of it is lost to our use, okay? It goes into the atmosphere. All right, I think everybody probably knows that. Which is the largest increase in temperature, okay? Look at these scales here. We haven't talked about them yet. Both B and C are the same because they both are based on the Celsius scale. We find Kelvin from Celsius, and 1 degree Celsius, by the way, is 1 Kelvin. Notice it is not to any kind of degree, okay, because it is absolute temperature. All right, now, So when we want to look at efficiency of a system, this is how we calculate it. What you get and what you had to pay. In other words, we could call this work out and the work we put in. Of course, we're always going to put a whole lot more work or energy into a system than we get out of a system. For example, again, going back to using the car, we fill up our gas tank and, we burn that gasoline. Well, we find out that, we didn't get as much out of the car that we wanted to. Well, why? Because the engine is not 100% efficient. Okay, it's just not. Okay, so reductions in efficiency, of course, are caused by process limitations and fundamental limitations. Again, if you think about what they talk about process eliminations due to practical details, that could be how much is the engine getting enough air and so forth. Are your tires in good condition? Is the engine lubricated properly? Fundamental limitations cause an energy loss due to physical laws. Okay, in other words, it's just a thermodynamic fact that when you take something and it cools, okay, we know that some of that thermal energy goes into the surroundings. Okay, so again, the efficiency of our objects are based on those two limitations, process and fundamental. Again, process, just listen to the word process. In other words, how it functions. Okay, all right. So notice this, 35% efficiency is close to the theoretical maximum for power plants due to fundamental limitations. Okay, so you mean to tell me that we burn all that coal and we only get 35% of the energy out of it? Yep, that's what they say. Of course, that would be an average. So, unfortunately, we lose a lot of the energy. Okay, now, here it talks about how to solve efficiency problems. I'm not going to read this to you. Again, it goes back to the equation, what you get out of it and what you put into it, divided by, and then of course you multiply times 100 to put it in percentage. Let's look at an example here. We've got a 15-watt compact fluorescent bulb and a 75-watt incandescent bulb. Each produce 3 watts of visible light energy. What are the efficiencies of these two types of bulbs for converting electric energy into light? Now you're fixing to find out why everybody's going to fluorescent. Okay, well, we know that 15 watts is actually 15 joules per second, right? So the 3 output, let's see, let's go ahead to the final page. So we solve it. So the fluorescent bulb uses 3 joules of energy. Okay, what we get out of it is 3 joules. And what we put in it is 15 joules. Okay, so that's a 20% efficiency. That's pretty good, isn't it? Man, look at this incandescent though. We got 3 joules of energy out, but man, look at how many we put in it. We put in 75 joules of energy. So we get a 4% efficiency. So you can see now why practically all commercial buildings, state buildings, federal buildings, city buildings, county buildings, that's why you go in all school buildings. They are all fluorescent lights now, have been for many years. Now way back yonder, they were incandescent. Of course, fluorescent hadn't been invented yet. For the past probably 40 years, 50 years maybe, we've used fluorescent bulbs in all of our school buildings and state and federal buildings. Okay, it's just much more efficient, and that's why. The only problem with that is fluorescent bulbs contain mercury, and we throw these things in our landfill, and that is not good, but they are very efficient. Now, energy in the body, and I'm just going to quickly go through this. We all know that we get chemical energy from when we eat foods. Now, not all foods contain glucose, but plant matter does, and of course that includes sugars. Okay, Sugars are a complex form of glucose. You have sucrose and fructose. And you hear probably a lot of that in the news of high fructose corn syrup. But plain old simple sugars, what we call glucose, are produced in plants. Plants use glucose. Actually, our body takes glucose and oxygen and converts it into carbon dioxide, water, and energy. Now, the reverse of that is that plants take CO2. Plants use CO2 and water and the solar energy, along with the help of chlorophyll, the aid of chlorophyll, and converts into oxygen and glucose. Okay, and plants store that glucose to use. But mostly it's stored as starch many times, and we eat that. That's what we enjoy about it, like a potato, okay? But our bodies run it this way, okay? And of course, that is what we actually need to make our body function. We release the CO2, and we do use some of the water, and we also release water too, all right? Now when we transfer or what we call burning food, of course, all of its energy will convert into thermal energy, okay? It all goes to thermal. And we measure thermal energy in units called calorie. 1 calorie is equivalent to 4.19 joules, actually 4.186. I'm old school. 4.186 joules is 1 calorie, and that's, of course, the System International unit, the SI unit. And when we look at what are called food calories, now let me write this down. Food calories, what we call big calories, or food calories, okay, is actually 1,000 calories. In other words, 1 food calorie is equal to 1,000 regular calories, okay? And so when you look at for example, if you look on a pack of cookies or whatever, and man, I hope it don't have 38, but anyway, that's the amount of energy, the amount of energy in 1 gram of fuel in kilojoules, you can see here. But now when you look on, let me go back to that. When you look at food packages and it says 250 calories, okay, let's say a pack of cookies, all right, that you buy in a vending machine, 250 calories. Now I'm just making that number up. What does that actually mean? It's actually 250,000 calories that are in that particular food item, if that's what it is. So it's amazing how much energy it takes to make our body function. Okay. Now here we're getting energy from different products. Here we see in 1 gram, just in 1 gram. Y'all, that's a gram is extremely small quantity. Notice how many kilojoules. Hydrogen, man, we get a lot out of hydrogen, don't we? 121. That's one of the reasons they use hydrogen as a propellant for any of our spacecraft. That and oxygen mixed together. Hydrogen, we get a tremendous amount of energy. Gasoline, notice gasoline, we just don't get the energy out of gasoline that we do some of the other fuels, okay? But it's easy to refine, and it's cheap to refine, and we use it. And I know some people are just, they're just off the wagon about let's do away with all fossil fuels. Folks, we can't do that, okay? We're always going to need fossil fuels in some capacity, all right? So there's so many things that we use petroleum for that really cannot be synthesized. We can make biodegradable plastics, but the thing about it is there are times when we need plastics that are not biodegradable, okay? So we need fossil fuels, okay? Coal, notice coal is less than gasoline, about almost half. Carbohydrates in food, and then wood chips. I hope nobody's chewing on wood chips, but anyway, maybe a groundhog or a beaver might be chewing on some. Here we see the contents in a particular foods. Carrots. Notice carrots have a very low calorie intake. Fried eggs, apples, beer, barbecue chicken. Oh man, I'm getting hungry there. Latte. Notice pizza. Ooh man, it really starts going up. And then of course fast food meal, burgers, fries, and large drink. You realize that one fast food meal, you almost get a daily supply of calories. That is crazy. And the bad problem with that is if we eat 3 meals a day and one of those are fast food, we are getting entirely too many calories in our body if we're not very, active and working out a lot, okay? All right, now at rest, of course, believe it or not, and I hope you should know this, if any of you have had biology, we do use energy, believe it or not. We have to, y'all. If we didn't, we'd die, okay? Notice it says about 100 watts of energy at rest, okay? Here we see our resting power. Notice how much the liver uses. Wow. The liver uses 26. Now, this is for a 68-kilogram individual. 26 watts of power just resting, okay? The liver is one of the most important organs in the body, and most all of you should know that from your biology in high school and college. Then the brain is second highest, heart. Actually, the brain and the remainder of the body is tied, but the brain is second highest. The heart is 7. Notice it doesn't use much. Kidneys, 11. Skeletal muscle, 18. And the remainder of the body is 19 for a total, of course, 100. Now, okay, so let's move on. I don't want to talk about that, all right? And you can read that if you want to. Here's the efficiency of the human body. How would we calculate that? Well, first of all, we want to find out how much energy it takes, how much potential energy there is if a 68 kilogram person climbed a 2.7 meter high staircase, and on average we use 7,200 joules to climb the stairs. So how efficient are we? We are about 25% efficient, okay? Isn't that crazy? So you mean to tell me that we're 25% efficient? Well, where in the world does the rest of it go? Well, it goes to run the body. Okay? All right. Okay, now, let's look at temperature scales. Now, anytime we look at thermal energy, of course, thermal energy, which we actually call temperature, or we measure it, by temperature, of an ideal gas is the total kinetic energy of the moving atoms within that gas. Now, how do we define temperature? Temperature is simply defined as a measure of the average kinetic energy of the atoms that make up a gas. Okay, so if you have an ideal gas and you want to measure its temperature, you're actually getting an average measure. If we put a thermometer in a room, I say it's an average measure. It's an average measure of the area it's near. Now, if you go from one side of the room to the other, you're going to find sometimes great discrepancies in the temperatures. That's why in the old days they had the old radiator system, and if you sat by the radiator, you probably, got too hot, and if you were on the other side of the room, you froze to death. So, that's just kind of the way it was in the old days, okay? All right, so temperature, again, you need to know what the temperature is, how we define it. It's a measure of kinetic energy, average measure of the kinetic energy, okay? If you had a steady force, here's a little quick question. A quick check. Steady force pushes in the piston of a well-insulated cylinder. In this process, the temperature of the gas is going to do what? All right, we are applying a force. In other words, we are doing work. We are doing work on the gas, right? Well, what do you think is going to happen? Well, I hope and pray to the dear Lord you say that it is going to increase because, look, there's no heat, so that term is gone. It's zero. So work is equal to the total change in thermal energy. So if you're doing work on the gas and it's really insulated, and guess what? The temperature is going to go up. Okay? I mean, come on, y'all. How in the world do you think a diesel engine works? It compresses air to a very, 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 very small volume. Well, the engine is doing work on the gas, okay? It's doing work on that gas, and when it compresses it and compresses it and compresses it, the diesel fuel with the air mixture, once it gets to the flash point, it ignites, okay? And that's why diesels have very high compression, okay? It's also why they create a lot of power, too, all right? Now, okay, so we look at the temperature scales. Now, I do not like using the fractions. If you want to convert from temperature Celsius to Fahrenheit, here's what I like to use. Temperature Celsius is equal to, make sure I do this right, it is the temperature Fahrenheit minus 32 divided by 1.8. Okay? That's how to convert to Celsius temperature. And then to convert to Fahrenheit temperature Fahrenheit is equal to temperature Celsius times 1.8 plus 32, okay? And of course this we want to do first. All right, so you take the temperature Celsius, let's say it's 5 degrees Celsius, so 5 times 1.8 would be what? 5 times 1.8 is equal to 9 plus 32, you get what? 41 degrees Fahrenheit. If we wanted to convert Fahrenheit to Celsius, let's say it's 50 Fahrenheit, so 50 minus 32 is 18, and 18 divided by 1.8 is what? 10 degrees Celsius, okay? Now, okay, so that's how you do it. Now, if you've ever noticed, and when we look at temperature scales, and you do need to write those on your formula card, by the way, when we look at the temperature scales, and we talk about absolute zero, well, when we look at, let me go back a minute. Let me go back here. If you look at the temperature scales, and you look at Fahrenheit, we know the boiling point on Fahrenheit is 212. The freezing point, the ice point, this is the boiling point, and this is the freezing point, is 32. On the, I'm writing them backwards, doggone it, the Fahrenheit scale is 212 degrees Fahrenheit, and then 32 is the freezing point, isn't it, okay? So this is the BP and the FP, right, okay? And on the Celsius, it's 100 degrees, now this is for water, Celsius, and 0 degrees Celsius, and that's the boiling point, and the ice point, or the freezing point. Well, let's do some subtraction here. Notice we get a difference of 100. Here, we get 180, okay? Now look, now what is the ratio of Celsius to Fahrenheit? Well, take 180 and divide it by 100, notice we get 1.8. Now that should jump out at you because I was using that in the formulas, okay? So notice that for every degree Celsius, it's almost equal to 2 degrees Fahrenheit. Does that make sense? So 1 degrees Celsius is approximately equal to 2 degrees Fahrenheit on the Fahrenheit scale. Almost, 1.8, okay? And that's why if you ever hold a Celsius thermometer besides a Fahrenheit thermometer and look at the scales on it, you'll notice that the Celsius thermometer, there's fewer marks on it, and they're farther apart, okay? That is why, okay? Now you see why we use 1.8. And by the way, when you looked at the equation here I just wrote, we do the temperature Fahrenheit minus 32 divided by 1.8 to find the Celsius temperature. Why do we do that minus 32? All right, y'all, that's to adjust for the difference in ice points. Ice point on Celsius is 0, ice point on Fahrenheit is 32, so we have to make an adjustment for that, okay? All right, now, when we look at the Kelvin scale is the point at which kinetic energy of all the atoms in matter is going to be 0. We call this absolute zero. Now notice there's not a little degree sign there on Kelvin. We do not say degrees Kelvin, okay? That is a no-no. Why? Because it is, when we read Celsius, okay, it is to the Celsius degree. In other words, it's what the professor, well, I don't know if he's an instructor, he probably was, what Mr. Celsius and Mr. Fahrenheit came to when they created their scales, okay? There's also another scale called the Rankine scale. They use that a lot in engineering, but we won't get into that, but I just thought I'd throw that out there. Okay, and it's based on the Fahrenheit scale, but it's also an absolute temperature scale too, the Rankine scale is. So, but typically we use when we talk about absolute zero and the Kelvin scale, we use that for all of our thermodynamic calculations. We can use Rankine, but usually we use Kelvin, okay? Okay? And so at 0 Kelvin, folks, notice the temperature for the Celsius is minus 273 Celsius, okay? And that means that all molecular motion, all atomic motion has ceased. It has stopped, okay? So how do we find the Kelvin temperature? We use that simple little equation. Here's another one, 2 more to write on your formula card. To find the Kelvin temperature, it's Celsius plus 273. So what if it was negative 20 Celsius? Then it would be what? 253 Kelvin, wouldn't it? Okay? 253 Kelvin, and that's how we would do that. Then if we want to convert to Celsius, from Kelvin, we just take Kelvin and subtract 273, okay? It's that simple. So if it was if it was 100 Kelvin, what would it be? Ooh, that'd be what? That'd be negative 173 degrees Celsius, wouldn't it? Yeah, sure would. Okay? So please, please, please remember that, all right? Okay, I hope that helps you on those. Those are easy, all right? That's easy. All right? Now, quick check. Which is the largest increase in temperature? Well, I hope you say these two. I think we've already had this question asked. Yes. Okay. And now let's talk about thermodynamics. What is heat? Well, thermodynamics is, of course, the relationship between heat, thermal energy, and heat. And, of course, we also have to throw in other forms of energy there. Now, remember that heat is transferred between two objects because what? Because of a temperature difference. Now, remember that heat is a process of transferring thermal energy. It's a movement of thermal energy, okay? So heat is just kind of a word we use that when we're talking about the movement or transfer of thermal energy, okay? Please remember that. Now, okay, so remember too that heat always flows from the hotter object to the cooler object. I mean, it's impossible to do it without adding energy, okay? All right, now thermal energy, of course, is transferred from the faster moving atoms on the warmer side to the slower moving atoms on the cooler side. Eventually we get to what is called the zeroth law of thermodynamics, in other words, where they are all in thermodynamic equilibrium, okay? Now, or thermal equilibrium. If they are in contact, notice that from energy will transfer from the hot to the cold until both temperatures are the same. We call that thermal equilibrium. Now let's look at the first law of thermo, which basically says what? It says that for systems in which only the thermal energy changes, the change in the thermal energy is equal to the energy transferred into or out of the system as work, heat, or both. In other words, the total thermal energy, the change in thermal energy is equal to the work plus that's done on it plus the thermal energy, okay? And what we call heat is Q. You could put an H there if you wanted to. Typically we use Q in physics, okay? And so there's another equation to put on your formula card. Please remember that. And how do we define that? Well, it's basically a statement of the law of conservation of energy, okay? So if you're doing work and you're adding heat or taking heat away, then the thermal energy will be equal to the sum of both of those. All right, now, when we look at energy diagrams, notice right here we've got a fire. It's heating up the copper bar. The energy's transferring down. And guess what? It's going into the ice, isn't it? Well, what do you think the ice is going to eventually do? It's going to melt, isn't it? So we have what's called a hot reservoir and a cold reservoir. And by the way, in both situations here, by definition, QH and QC are positive quantities. And you say, well, how is that the case? Well, because, look, energy is being added into the bar. That's positive. All right, notice Q cold. Well, the ice is cold, but energy is going into the ice, okay? Okay, so they both are positive quantities, okay? All right. All right, so we got a negative 20 degree ice cube is dropped into a super insulated container holding a small amount of 5 degrees Celsius water. Then the container is sealed. 10 minutes later, is it possible that the temperature of the ice cube will be colder than negative 20? Oh, come on, y'all. What do you think? So you're telling me we're going to put negative 20 into 5 and it's going to get colder. Could it get colder? Come on. Absolutely not. It's not going to get colder, okay? It's just not going to, all right? Okay, energy transfer diagrams. Notice that that hot always goes to cold. Very simple, okay? Very simple. And this does not happen. Spontaneous transfers go in one direction from hot to cold, not the other way around. It doesn't go from cold to hot. Spontaneously, okay? All right? Spontaneous transfers. In other words, without you doing anything. Okay, it just spontaneously does that. All right, what is a heat engine? Let's look at heat engines. A heat engine is something that takes some of the energy as it's transferred and converts it into other forms. Give you a good example of a heat engine is like a internal combustion engine. That's considered a heat engine, okay? Lawnmower engines, of car, truck, so forth, okay? Now notice this. They take energy as heat from the hot reservoir, and then it turns into some useful work and exhausts the balance as waste heat into the cold reservoir. So think about your car engine. Notice that the pistons are moving, so guess what? There's where we're getting the work out of it. What happens to the rest? Well, it goes out the tailpipe, doesn't it? It goes out the walls of the engine into the atmosphere, okay? So that's how we look at that. And notice here that QC is equal to QH minus work out, okay? All right, important to remember that. Now, so we look at heat engines. Here we have, this is like in a steam generating plant like they have down in Gadsden and other places around Alabama and the country. They take water and they boil it, okay? They take it and they boil it, and they take it and boil the water, turn it into steam, all right, hot, okay? Now notice what happens. It turns the fan blade, creating electrical energy, and then of course it's lost. Some of it is lost back into the river. Y'all, I need to take a quick break. Sorry. Okay, so you can see energy going in to boil the water. We turn the turbine, create electrical energy, and then lost as cold. Okay? All right. Now, sorry about that interruption. Let's move on. So, how do we find the efficiency of a heat engine? Simply put, work out divided by the hot thermal energy, or QH minus QC divided by QH. So here is another equation that you can add, and of course if we want to find the work out, it's QH minus QC. That's how you can find out how much work we will get out of an engine. So there's you some more equations that you can put on your formula cards, okay? All right. Now, please understand, no heat engine can operate without exhausting some fraction of the heat into a cold reservoir. It just cannot happen, okay? It has to release it, okay? It'd be like your car engine not releasing the excess heat. It wouldn't work, okay? Now, when we look at maximum efficiency of a heat engine, now this is maximum efficiency. Notice that it is, of course, why 1? Well, of course, 100% is the maximum of anything, but we know we're not ever going to get 100% maximum, so we take 1 and subtract it from, because you're going to get a fraction here or a decimal. And so here's another equation that you can write on your formula card. 1 minus TC divided by TH, okay? Now, the following pairs of temperatures represent the temperatures of hot and cold reservoirs for heat engines. Which heat engine has the highest possible efficiency? Okay, well, which one do you think? Well, look at those temperatures. It's very obvious that okay, it's very obvious which temperature it would be, and that's the 300 minus 30 Celsius, okay? All right, the efficiency of this heat engine would be what? Well, I hope you see that it is 0.4, okay? 0.4. All right, temperature hot minus temperature cold, okay? 40 divided by, 60 divided by, 60 divided by 100 minus 1, 1 minus that, okay? All right, heat pumps and refrigerators. Transferring heat energy from a cold reservoir to a hot reservoir is what we call a heat pump. So we're going from cold to hot. Notice it takes work going in. That's electrical energy. We have what is called the coefficient of performance of a heat engine. And how do we find that? We use this equation right here. We say COP max is equal to the temperature cold divided by the temperature hot minus the temperature cold. We can also find it by looking at QC divided by the work that goes into the engine, okay? So please write this equation on your formula card. All right, and again, we see the same thing, that in both cases, a larger coefficient of performance means a more efficient heat pump. Same equation. but of course we want to have that efficiency number go up. All right, we got a Peltier cooler is a heat pump that can be set in either cool or heat its contents. One such cooler uses 100 watts of input power, whether heating or cooling. Which is the greater in coefficient of performance for cooling or its coefficient of heating? Of course, you can see it would be heating because QH is greater than QC. If you take this problem here and you're looking at your refrigerator, which is at freezing, 273 Kelvin, and then go to a temperature of 20, what is going to be the COP of this refrigerator? 13.6, okay? 13.6, all right? Now, entropy. What is entropy? Of course, entropy, anytime you have a spontaneous transfer of heat from hot to cold, it is an irreversible process. We've already said that. We've already said that. We've already defined what the second law of thermo is. The second law of thermo basically says what? That when an object, when energy is being transformed from one form to another, some of its energy is lost to what we call heat. In other words, we cannot regain that energy. It's not lost. In other words, it disappears, but we just can't use it, okay? It's impossible to regain it, all right? Talking about microscopic and macroscopic levels, microscopically, we see that you can have reversible reactions with macroscopically, but macroscopically, it'd be impossible to unwreck that car, wouldn't it? Okay? So, you know, we've got to understand that there are some cases that are just irreversible. So the second law of thermodynamics, the entropy of an isolated system never decreases. The entropy either increases until the system reaches equilibrium, or if the system begins in equilibrium, it will stay the same, okay? Now, what is entropy? Entropy is what? Basically, the law of disorder. In other words, all things in nature move towards more and more randomness, more and more disorder, okay? Again, if you take something that's hot, it cools off. You know, you take a piece of hot metal out of the fire, you set it down on the ground, on the table, it'll eventually cool. Everything moves towards more and more randomness and disorder. We find out that we do not, you know, if you take a building and just leave it empty, you know what will happen to that building? After about 20 years, it won't be usable. It won't even be that long. Probably after 10 years, you won't be able to use that building. Same thing with the house. The worst thing you can do to a building or a house is not use it. Same thing with the car. Why? Because of entropy, okay? All right. Anytime you convert energy into thermal energy, one form is converted to thermal, there is an increase in entropy. Again, going towards more and more disorder. Okay. Of course, that's why we can't have anything such as 100% efficiency. You have a large ice cube. It's dropped into a super insulated container holding a small amount of 5 degrees Celsius water. Then the container is sealed. 10 minutes later, the temperature of the ice and any water that is melted from the ice will be warmer than 20. This is a consequence of what? The second law of thermo. That's pretty easy. And I hope this quick lecture has helped.